So this is, I'm going to talk a little bit about a hurricane that hit Mexico in 2023. This is an above design level event. Okay, so we don't expect everything to survive that, but it's important to understand what's happening because the nature of these extremes is truly changing. So these are wind speeds that were above 330 kilometers an hour. That's faster than a Formula One car. So it's an extreme event. The design speeds in the area are about 150 kilometers an hour. So we would expect a lot of stuff to break. And the kind of things we see can really enlighten us about the storm. So in this image of a high-rise building, I'm going to show you a bunch of images, but the structural system, the main structural system, performed really well. It's the cladding and the panels and the windows that fail. And so you see lots of photos like this where you have broken windows and panels falling out of buildings. Of course, that's a significant life safety issue, and we need to be concerned about that. Types of failures, again, that you see, again, broken windows, you have partition walls coming off, you have damaged wall panels, balcony covers. All of this is failing, and so the people in the building are at risk. Here's some before and after images. I don't know if you're like me, you read the news, and I've been watching the terrible bombing that's been happening between Israel and Iran. I want to stay away from the politics, but you see images that don't look too dissimilar to this with buildings being destroyed. Again, this is caused by the wind, and when every window fails in the building, you don't really have a functional building any longer. Again, examples of this, walls facing the beach and panels coming off the sides, and you see this repetitive pattern over and over and over again. So this is what happens when we have extreme storms. Our structural system, the way we design concrete buildings, the way we design steel buildings is really good, right? They can withstand this far over design of the structure, but the cladding and the panels falling out means that these buildings have to be bulldozed at the end and rebuilt from the ground up. So we need to consider that. Lots of little details matter. This is a gravel roof. In North America, we use this quite commonly. So you put a membrane down and you put rock, gravel, ballast to hold the waterproof membrane down. Wind comes, it blows those rocks around. You often see the membrane falling off afterwards, but what it leads to is broken glass in buildings. So big surprise, if you throw rocks at windows, they're going to break, right? But that's one of our most cheapest and I'm going to say effective building covers, but it causes a lot of damage in the storm, so we have to probably move around that. I'm going to talk about tornadoes. Tornadoes are my passion. I love studying. This was a tornado that occurred just outside of Toronto. And you can see the kind of damage that it has. Tornadoes have a very narrow path. This was confined to 2 streets in the city. In North America, our houses are built from wood frames, but this is what it looked afterwards. We estimated the wind speeds that caused this to be about 200 kilometers an hour, a bit above the design. But what you see, first of all, the thing that catches your eye is all the debris and the chaos of it. But we want to study those patterns. We see a lot of the roof covering off, roof sheathing, and other damage like that. So that's what you see. This was a tornado that occurred about 100 kilometers from my house. Again, it was a pretty significant event. And you see the vehicle there with 2x4s, 2x4 lumber, 2 inches by 4 inches is what we commonly build our houses from. And you see all of that entering the vehicle. Someone was in that vehicle in the tornado, and they were unhurt, which is just lucky. But can you imagine how terrifying it would be for those spears to be coming through your window in the event? This is a characteristic of windstorms. So when windstorms, we have the cladding failures break, the panels fail, it has to go somewhere. It enters the wind field and it gets blown around and it causes cascading kind of damage. You can see debris impacts here. I don't know if you have a laser pointer, but you can see again the interior finishes. There's holes in the walls that were caused by debris, and that caused the roof failure that ultimately left by changing the loading on the structural system. Debris causes such damage, again, in a structure. This was a tornado in Joplin, Missouri in the United States. And this was what the aftermath of it. You can see the vehicles around, there's chaos around it. In fact, there was some vehicles on the roof of the building after the tornado, so it was a very significant event. Every single window was broken in this building, but the structural system remained perfectly intact. But 12 people were killed inside the hospital during the storm. So I ask you to think about, is this a fail as structural design, or is it something that we can do something about? I want to say that we can do something about it. So highlighted there were windows. This was the mental health ward in the hospital, and it had the safety glass with the metal wires in it. None of those windows failed. Every other window in the building failed except here on the mental health ward. And so what we can do is, it's going to cost a bit more money, but there are solutions for these kind of events. Okay? And keeping the envelope together becomes really one of the critical points for us. Again, just thinking about wood frame houses in North America, I realize you don't have structures like this here, but it highlights the point. In this case, the people that left their garage door open and the windstorm came, and that opening changed the pressure inside the building and caused the roof to fail. And so it changed the loading situation when the envelope failed. That roof entered the wind field and it hit the neighbor's house right beside it. That roof landed and collapsed that structure. And so you have this cascading kind of damage that occurs. We see the same thing if we go back to the Acapulco hurricane. You have windward windows failed in this case. The wind goes in, and when you add that with the external pressures going around the outside of the building that want to suck the cladding off, you end up with panel failures going out. And so this kind of cascading loading is really important. So the cladding, we don't think about it as being important for the structural system, but it's what transfers the load to the structural system, and we can change the loading on significant parts of the structure when the envelope fails. We see this over and over again. This was not a tornado, this was a hurricane. This is Hurricane Andrew in Miami, and this neighborhood was devastated. Clearly, nearly every single structure in the neighborhood was destroyed, and you see the debris field again lying around. About half the damage in windstorms is estimated to be caused by the debris flying around. And so it's really important, again, that we keep those elements in place. So, components and cladding. I realize I'm talking to a structural engineering conference. I understand that. But the performance of our buildings depends, in the windstorms, depends on the cladding systems. We need to keep the building enclosed. If we have a failure of the enclosure, it can lead to partial or complete collapse of the structures or elements of the structure. And we need to have accurate design standards for these if we're going to reduce the losses. And this is really important. One of the lessons we learned during the COVID crisis, for example, is we all go and shelter in our homes. When we have storms, we go and shelter in our homes. And so we need to be able to protect them. And so the sheltering in place is something that we need to consider. And one of the things I want you to think about is, do we have the right reliabilities for our cladding systems? I think we do for our structural systems. They perform in these over-design events, but our cladding is failing, often cladding at much lower levels. And so we need to think about that in terms of how we design things, how we handle our building codes, and what we design for. And again, the weather and the systems are changing, where we're building is changing. We need to think about that. So what can we do? I don't want to just be doom and gloom here about losses growing, and we have tools, and I want to talk about some of those. Wind tunnel testing. So the design of high-rise structures, most high-rise structures get a wind tunnel test because it saves money. This goes back to the 1960s. Professor Davenport and Professor Cermak developed the modern methodologies that we still use today for the World Trade Center towers, and we follow those. The World Trade Center towers were a revolution in design. They were such lightweight structures, and they were in a hurricane region. And so the modern methodology that we use for designing them with the wind tunnel is really well established. And we can use these all over the world for them. In typical wind tunnels, if you're not familiar with them, we have very long test sections, and basically what we're trying to do is simulate the wind at a scale. So we can make a scale model. You can see images. We have a scale model. You can see this is Hong Kong. If you're familiar with some of those buildings, we can make a scale model of that. We have to make a scale model of the wind that goes through the wind tunnel and match that. So this is a busy graph, but what it's showing you is how the wind changes with height in full scale, how the turbulence changes with height in the real wind, and we model that. Then we can consider how the building plays a role, and if we're going to design the structure, we need to think about the aerodynamics, and a low flat building, like a warehouse, like an Amazon center, for example, has different loads than a tall, thin, high-rise building. And if you have mid-rise buildings like you have a lot of in here in Granada, apartment buildings, flats, and things like that, you have different aerodynamics, so the shape matters. When the wind acts, see if this plays. This is a low-rise building. These are pressures on the surface of the building. The red ones are positive. This is so wind approaching from the left to right, approaching the building. The red colors are high pressures. The blue are low pressures, lower than atmospheric. And you can see that it's fluctuating. The loads are different on every surface of the building, and they're changing continuously in time. And so that's what we need to design for. And so we have tools for that. This is wind tunnel data. It's not a simulation. Well, it's a simulation, but it's from the wind tunnel. All right, so we have wind tunnels, and we can do things about that. But thinking back about the cladding, if we think about the size of that building in that photo, the size of those buildings in the wind tunnel, getting loads on the cladding is really, really hard. So small elements on large buildings is one of our major challenges. When you have things like solar panels, these are roof-mounted solar panels, you need to make much larger models, and it's changed the way we actually do wind tunnel testing now. To give you an example, if you're from Madrid, you might have recognized this building. This has a very complex double skin, and to test that in the wind tunnel, that double skin and the openings affect the loading on the building, so we need to know about that. But we need to design both the outer layer, the rain screen layer, and the inner layer. And so we develop different methodologies to do that. We test the whole building, for example, using a normal wind tunnel study like Professor Davenport developed in the 1960s. But then we can make a model of part of it, and we try to replicate just the flow around that part of the building in order to get better analysis of the loads for the cladding system. So it takes more resources, it takes more effort, but that's what it takes to actually get the loading. Things like solar panels. I was amazed flying into Granada. You see olive trees and you see fields of solar panels. It's really quite remarkable, the amount of solar you have in this country. I'm just astonished by it. So you can get loads on those things again from the wind tunnel, and it's important to optimize the design to reduce the cost, and one of the major parameters for design is the wind loading. And so you have to do this, but we have special techniques, and often these are roof-mounted solar panels. The small gaps between each of the modules actually controls the loading, and so when we make a wind tunnel test, we have to be able to model these tiny parts and get the loading. But we have methodologies to do that now, and they can provide that with quite accuracy. And then the different nature of storms. We need different types of facilities. So this is our tornado simulator at Western. It's the largest tornado simulator in the world. And we can simulate things like this, tornadoes now in the wind tunnel using the same methodology. The model that you're seeing there is of a part of Ottawa. Our national capital in Canada was hit by a really significant tornado a few years ago. In fact, I have video of the tornado passing past our parliament buildings, which is something no one ever thought we would see. But from this information, we can get the same aerodynamic information that we have, and we can start to design for tornadoes. And we're actually working on incorporating tornadoes into the Canadian Building Code now, because it's a really important part of it. One of the things that's changing, as engineers, we design individual buildings. Storms like this, because of the debris and what they're doing in the community, makes us have to think about it in a different way. And so part of what we're doing in developing code provisions for tornadoes is thinking about the extent of the storm. So the probability of any particular building being hit is really small. The probability of a community being hit is much higher. I live in London, Ontario. I've lived there for about 30 years. We've had 2 tornadoes in our city in my time there. And so we start to think about what is the community resilience requirement for design, and when we're thinking about those kind of elements when we put things like this in the wind tunnel. So again, it's changing our philosophy of design a little bit, but it's something that we should be thinking about. And then testing cladding. There's standard tests for cladding, and these are used in architecture and by people using the building products. But we can use more advanced methods to optimize design so we get the right reliability level. This is testing of a metal roofing system and a failure of the roofing panel. You can see how the panel fails and eventually pulls from the clip attached to the purlin. Debris, we talked about the debris thing. Again, the 2x4 hitting our windows. That window survived, right? It's still intact, right? So it did its job in this case. So we can find things that do that. Just again, this is a North American example. We have the 2x4s, and this is what the structure looks like. And so when that starts to come apart, this is our major debris element. The 2x4, the wood is very light. And we've done wind tunnel tests that shows that when you have wood elements in the wind field, they will fly at the same speed as the wind. So if you have a 200 kilometer an hour windstorm, you have 2x4s flying 200 kilometers an hour. And that's why debris is such a big deal, and that's why we need to hold the building elements together, and we can withstand it. And obviously if you have concrete panels, that's not a bad solution, but you still need to have windows because we need to be able to look out them and manage that. So we have a whole range of tools that are emerging and that are being established, and it's changing, but it's changing the way we need to think about design for extremes. So the extremes are changing, and as engineers, this is what we need to think about in the future. Cladding and the building components on the outside of the building are the key aspect for storms. Of course, that keeps the weather out. It keeps our cool air from the air conditioning in and the hot air that we have here in Granada out, right? So it plays that role, but it also in the storm, it protects the building. And by holding buildings together, we hold the downstream buildings together from the windstorm. So this requires different tools. It requires a different philosophy of design, but we have those tools. And often, as you know, as an engineer, we can often find solutions that are not expensive when we put our engineering brains to work for these things. We can find solutions that don't cost more, but when we understand the risks, we need to understand the risk to achieve that better performance. And as the climate keeps changing, as the population keeps growing, we need to think about this. And so it really is, I think, about getting the right reliability levels for the nature of extremes that we have in our future climate. And with that, I will stop and say thank you. And again, I'm really honored to be here and happy to take questions if we have time.
Thanks a lot. Thank you very much for being here, for such a fantastic talk, so enlightening. Pues muchas gracias. Me dicen que vamos bastante justos de tiempo, con lo cual vamos a dar paso ya directamente a la entrega de premios que está agendada. Muchas gracias.